facility with a virus in a program, an infected program, on a floppy. And just when he sets foot in the facility, if he's caught with it and it's analyzed, he says, oh, I didn't know I had a virus. Sorry. I didn't write it. Usually I better scan my hard drive. Okay, so that's the idea there. So the guy runs it, on the machine, and runs the program on the disk, and the disk installs the Trojan, and then the Trojan's in there, and it starts doing its thing, and it goes home and just sits tight for a while. And what the virus does is, again, well, the virus installs the Trojan. What the crypto Trojan does is it uses its public key to encrypt the log and password pairs that it sees during this time interval. It stores them in a hidden password file, but it uses a very specific data format for this password file. It uses a circularly linked list. And every time it adds the new asymmetric ciphertext of a login password pair to the list, it overwrites the element in the list. So it always contains the freshest set of user logins and passwords. And that's important. One of our goals is to not give away the presence of the Trojan. And to meet that goal, we ensure that the hidden password file never changes in size. Okay. So now we have this extra level of privacy too, because anybody who haps upon this hidden password file is just going to see a bunch of asymmetric ciphertext and it will be indecipherable. The attacker's faced with the problem of going back, when his heart's racing on his way back, a little adrenaline, and downloading this hidden password file, right? Because he can get busted there. Maybe it was found. Maybe special hidden software alarms are now waiting for this criminal to return. Okay, but actually, with that problem in mind, the Trojan is designed to do the following. Every time a writable or media is put into the drive, and the last few sectors of this media are unused, the Trojan unconditionally copies the hidden password file to the last few sectors and leaves them marked unused. What does that mean? That means everyone who inserts a writable floppy into this gets the file. It's the difference of push versus pull, uploading versus downloading. So the guy comes back, he inserts a blank disk, he writes a letter to his girlfriend. What if he was busted doing that? Well, how can you bust him? That probably happened to 100 people over the last 2 weeks. That's all they did. So that's the idea, and we call this deniable password snatching. So he goes home, he busts out, Norton disk utilities or whatever. He carefully extracts these sectors, and then he decrypts them with the private key. And only he can do this, because only he knows the proper private decryption key. And this extends to network-based attacks and things like that. Okay, so again, all I really did here was review deniable password snatching, but this experiment is about perfect questionable encryption. So what's that all about? Well, we can improve the attack even more. And the idea is as follows. We want to obfuscate whether or not the Trojan is actually encrypting anything. Okay? So it starts calling RSA, it makes calls to AES. While it's doing this, say if it hybrids encrypts the login password pair. At the very least, it needs to call an asymmetric encryption function like RSA. So you can watch it do that in IDA Pro or OllyDebug or whatever. So we ask the following question. If you take core dumps of this Trojan passing plain text and a public key to the asymmetric encryption algorithm, this is the public key within the Trojan, is it performing encryption? Is it theoretically preserving the login and password pairs of the users after this mathematical transform is applied? In other words, can you prove that the malware has been used to steal data? This has everything to do with the algebraic structure of the public key, which might be bogus. Okay, that's the idea. So here's the question kind of revisited. Does the malware code and core dumps of its operation prove that theft has occurred? Answer. Not necessarily. In any public key crypto system, the attacker can generate a key pair, throw away the private key, and have some witness that witnessed him throw away the private key. Then he's not getting a hold of the plaintext. So in some sense, one might argue he's not stealing it. Okay, so I'm not going to get into legal stuff here. All right, there's a huge problem with this. Obviously, what jury's going to believe? What jury's going to believe that this private key was actually destroyed? Okay, so that's kind of a stupid argument and that. possibility. But let's ask the question again now with a different public key crypto system. Let's ask the question with El Gamal. Okay, so does the malware code and cordons of its operation prove that theft occurred when the El Gamal public key crypto system is used? El Gamal has a very kind of crazy algebraic property that it's possible to sample public keys using the exact probability distribution and from the exact set as the way these key pairs are defined. Okay, it's possible to sample a public key randomly knowing the corresponding private key. Okay, you can choose Y randomly without knowing X. And that's a bit different than claiming it was throwing away. It's claiming that you sampled Y randomly and never knew X. Okay, but again, it's the same basic kind of problem. Who's going to believe that the attacker sampled Y without computing Y equals G to the X for some X that he knows, which is the El Gamal private key? Okay, so those are obviously very weak, but interesting sort of things to. So Modi and I introduced the notion of a real and versus a fake public key, and we managed to squeeze it into our book that we published in 2004. So we define a real public key as a public key that produces decipherable encryptions, a correct public key. We define a fake public key as one that produces information theoretically indecipherable encryptions with respect to everyone. There is no private key that can decrypt encryptions of such public keys. They're perfectly useless in some sense, but obviously they're not useless, otherwise, I wouldn't be talking about them. So a real public key produces decipherable encryptions, a fake public key produces indecipherable encryptions. So the attacker chooses which one to put in the malicious software, real or fake. However, one of our requirements of a fake public key is that it looks just like a real public key. And that is a very specific meaning in computer science. What we mean is that under a specific intractability assumption, there does not exist a probabilistic polytime Turing machine that can distinguish between a real public key and a fake public key. Okay, and that obviously requires proof. And our questionable encryption construction has the property that the attacker has the exclusive ability to prove whether the public key in the malware is real or fake, and he can prove it at his own discretion. Okay. So we presented this at, after we went over it in our book, we worked through some of the details. We presented it at MyCrypt in Malaysia, and it's now the subject of an IEEE Transactions Journal paper. Our construction is based on the Palliere public key crypto system, which has some really amazing algebraic properties. And so what our construction looks like is as follows. We add a brand new key generation to Palliere. We call it the fake key pair generation algorithm. And what it does is it produces a fake public key on output, and it also outputs what we call a witness of non-encryption, which is a poly-sized value that proves that the public key is fake and can't be used to decrypt anything. There's also, along with Palliere's three algorithms: key generation, encryption, and decryption. Palliere key generation is the real key pair algorithm. It produces a public key that produces decipherable encryptions. We add another function to Palliere in this construction, and it's a predicate function f that returns 0 or 1, and this function takes as input a public key and a witness. Okay, so the witness of encryption is the private key, a normal Palliere private key. Okay, so there's a fake public key and a witness of non-encryption, and then public key, which is a normal Palliere public key, and then the Palliere private key, which is the witness of encryption. So the predicate f takes as input a public key and its corresponding witness, and it outputs 0 or 1. Okay, it basically decides whether the public key is real or fake. And also another security property for this construction is that it is impossible for a public key to be both real and fake at the same time. Okay, so the attacker can't cake and eat it too. If the attacker puts a fake public key in the malware, and the malware is used to encrypt data and transmit it, the attacker cannot recover that data. Provably so, the attacker cannot recover that data. Okay, so the details of this construction are outside the scope of this presentation, but it behooves us to mention that this notion is related to, but different from, other notions in cryptology, namely oblivious transfer, all or nothing disclosure of secrets, and deniable encryption. So enough with all these nitty-gritty details. Let's talk about an attack scenario. So here's the attack scenario. The attacker generates a real or public key. The attacker places the public key in the Trojan. The Trojan encrypts, in quotes, encrypts stolen plaintext and covertly broadcasts it. If the public key is real, then the attacker reads the broadcast, deciphers it, and obtains the plaintext, because he can. If the public key is fake, then the attacker can't read the broadcast, doesn't even try, and this is a form of spoofing attack in that case. So what good is this, right? In one case, he fails to steal data. Well, let's back up. Let's take the 10,000-foot view of this, okay? Suppose there are hundreds of people doing this, some of which use real public keys, some of which use fake public keys. A prosecutor cannot prove that the malware a processor cannot prove that malware transmits plaintext from the host computer system. How can they? The prosecutor must prove whether the public key is real or fake. Right? Burden of proof. Right? So that's really it in a nutshell. Okay. It may be possible to prove indirectly, okay, that this malware was used to steal data. Okay, so maybe the accused is, made 1,000 fraudulent credit card purchases, and there was essentially no other way that he could have obtained the credit card number, so you can infer indirectly that it came through the malware, whatever. There may be indirect ways. This cryptographic technology makes it impossible to prove directly that such malware steals data. An attacker may take the fifth and refuse to reveal the witness of encryption or non-encryption, whichever the case may be. And the basic idea here is that this attack can set a precedent that malware that appears to encrypt data and steal it, in fact, does not. Right? So maybe hundreds of people can do 75 of which use a fake public key. And after 2 years, after Symantec and McAfee and all those guys have studied these attackers anonymously publish the witnesses of non-encryption that's on bulletin board somewhere. And then people execute it through the predicate function F. And they, in fact, verify that these are bogus public keys. They're fake. It could have possibly stolen from people who were infected with this virus. So it's even possible to set precedents, without a single court case in this kind of thing. So, okay, so we implemented this. The implementation is in ANSI C. It uses OpenSSL as the underlying crypto library. It uses the minimalistic GNU for Windows Development Suite. To do this, we implemented Polyere key generation, encryption, and decryption ourselves. OpenSSL does not currently have Polyere at all in it. We also implemented the predicate F and the fake key pair generator. And our experimental implementation is actually capable of encrypting full-on files. And it uses Polyere and also Blowfish in cipher block chaining mode. Okay, I'm not going to get through all of these. So I am skipping experiment 3. If any of you are interested in crypto counters, please see me. And now I'm just going to move on to the last one, tagged private information retrieval. So one can think of two password snatching scenarios. An indiscriminate case and also a case that discriminates on which passwords we're after. In the indiscriminate case, we want everyone's password or no one's password in particular. In the case that discriminates, we want the password of a particular user. Obvious desirable properties for this are we want the hidden password file to be confidential, so that implies the use of asymmetric crypto. We want the Trojan to run